I'm visible now?
Yes, sir, you are visible.
Yes, sir. I'm ready. We are ready to start the session. Okay. Today, the topic is meta-heuristic role assembling learning. We are inviting distinguished faculty from the NIT Warangal. Thanks for your acceptance for a short span of time with your kind acceptance, sir.
Okay, thank you. Okay.
At the same time, we are introducing Dr. Ramalinga Swamy Cheruku, received the BTech degree in CSE from JNTU University, Kakinada in 2008, and MTech degree in CSE from Indian Institute of Information Technology, Galway in 2011, and he obtained his PhD degree from National Institute of Technology, Goa in 2018. He is currently serving as assistant professor in the Department of Computer Science and Engineering, National Institute of Technology, Warangal, Telangana. Prior to this, he worked as assistant professor in the Department of Computer Science and Engineering, IIIT, Naya, Raipur. He is also worked as an assistant professor in Mahendra University, Hyderabad, and served a database developer at Tata Consultancy Services for 2 years. He has published more than 50 research articles to his credit. He is acting as reviewer for several top-notch journals like IEEE, TIM Expert System with Applications, Applied Soft Computing, and Soft Computing, etc. He has delivered nearly 100 guest talks in various venues. Sir, extremely thank you for your kind acceptance. Please, over to you, sir. Please share your PPT and delivering the session, sir.
Thank you, Bosubabu, sir, for introducing me to the participants. And
Yes, sir.
yeah. So, is my presentation visible to you? Is everyone?
Yes, sir. Yes, sir. Yes, sir.
The meta-heuristic algorithms based ensemble models. Okay.
Yes,
Okay.
sir.
Okay. So, very good afternoon to one and all, and I'm myself, Dr. Ramalinga Swamy, and today I'm here to discuss about the some of the important topics, and which is one of my research scholars recently is carried out his PhD thesis on this specific topic, and it has I feel that it has a large potential, or it has many number of applications in various domains. Okay, so that's why I picked up this topic for the today discussion. It is called ensemble learning. So everybody knows about the ensemble learning, and it's one of the learning paradigm in machine learning area. So where we will combine the multiple classifiers. Okay, we are combining multiple classifiers. So then the question arises: how do we combine these classifiers? Okay, there could be we can connect these classifiers or combine these classifiers using serial and parallelly. And certainly there is a question about how many number of classifiers we have to choose, and how do we identify these classifiers. Okay, these are some of the challenges which priority in the ensemble learning. Okay, so to address this, today I want to give some light on the how we can address, how we can improve the ensemble framework performance by using meta-heuristic algorithms. Okay, the meta-heuristics are not new. These were there in since long time, but there are so many advancements in the happening, and the different versions of the algorithm. Different algorithms are being coming into the research domain year on year. So these meta-heuristic algorithms is a kind of algorithm that use some strategy to search for the global optimal solution. Okay, so it will use some heuristic, some technique to search for the global. So depending on the algorithm we are proposing, depending on the algorithm we are modeling for a problem, we will use the algorithm will use the specific technique for to arrive or to derive the global optimal or near optimal solution for a given a problem. Okay, So here the problem, we are there in the Ensemble framework. There exist multiple optimization problems. We can model it, and these optimization problems we try to solve using the meta-heuristic algorithm. So during discussion, so we will discuss some of the algorithms, some of the challenges which relate to the ensemble models, and then we will discuss how we can use how we can model these by using meta-heuristic algorithm. So this is the work carried out by one of the PhD scholars. His name is S. Srinivas. We recently completed a PhD, submitted a PhD. Yeah, this is very basic stuff about those before we begin about the ensemble. So we had in the long back, there are basic the ensemble techniques, namely the bagging, boosting, and stacking approaches. These are very old techniques. So in the bagging, we'll refer to the picking of the random samples, and these random samples are fed to the different the classifiers, and the output of these classifiers are aggregated at the last level. And in the boosting approach, what we are trying to do, we will gradually improve the performance of the weak classifier or weak learner over the ratio. Stacking is a combination of both the bagging and boosting. So in some sense, we can call it the bagging as a parallel approach, because so once we partition the data into different bags, suppose bag 1, bag 2, bag 3. So these bags are fed into the respective classifier. So there's no dependence among the classifiers training data. So we can train the classifiers parallelly. So that's the another important aspect of the bagging is that we can train the classifiers parallelly. In that sense, it is a parallel approach. So coming to the boosting, so what we are trying to do in the boosting is, so once we train the classifier and sequentially, the outputs or the misclassified samples of a particular classifier is fed as input to the next classifier. So such a dependency is there between the classifier. Means if at all, if I want to know, if I want to train the classifier, so I need to wait for the misclassified samples of the previous classifier. So this dependency will allow us to train these classifiers in a sequential fashion. So of course, if you are training a sequential fashion, that it will take more the training time. Okay, so we don't get benefit from the parallelism. Yeah, of course, the bagging has certain benefits and the boosting has certain benefits. So we can hybridize, we can define a new mechanism that will combine both properties of the bagging and some property of the boosting. So that is technique is called the stacking. So the stacking is a hybridization of both bagging and boosting. So this is 4 different problems that related to the what I can say that ensemble frameworks. So in the ensemble framework, what we are trying to do that. Let me show you that. Yeah. This is one of the ensemble framework. You can say it is a stacking approach. So we have used 2 levels of classifiers. So level 0 are classifiers and level 1 classifiers. So in the level 0 classifiers, the way we have trained the level 0 classifier, the namely base classifier 1, basic classifier 2, base classifier 3, we have used the bagging approach. Means we divide the data into different sets of bags, and these bags are independently trained by the different classifier. So in that sense, it's a parallelism, or in that sense, the bagging approach. Then what we did, so in the next level, so the outputs of these classifiers, so there are 3 classifiers, suppose that every classifier produce the probabilities of a prediction for a given task. So these are the probabilities along with the ground truth information of the original data is used as an auxiliary data set, and this data set used for the training of the the next level classifier. Here, that next level classifier or meta classifier or meta learner, we have used here the support vector machine. So to further improve the performance of these SVM, so we can again fine tune these parameters of the SVM so that we can improve the performance of the traditional SVM which we have used for training of this auxiliary data set. Yeah. So what we did, so in this case, so before we are feeding model, before we are using the stacking approach, into the proposed framework. So what we did here, so we address the problem of class imbalance. Suppose if the data set is having the class imbalance, so the minority of the samples are oversampled by using the appropriate techniques, SMOT or the binary SMOT or ADASIS or the ORWAY. So using the different multiple techniques are available, oversampling techniques. So these oversampling techniques are used for creating the balanced data set. Once the data set is balanced, so what we did here, we have used the 10-fold cross validation. We can use the 10-fold cross validation, 5-fold cross validation for partition of these data sets. So basically, these bags, we can nothing but we are creating a 10 bags, or if you are using 5-fold cross validation, we are creating these bags of size 5. Okay, so the number of bags of size 5. These the classifiers are feeded. I mean the bags, you can say the bags are created using full 10 FCV, 5 FCV. These data, the respective bag information is feeded for the training of the different classifiers. So the classifiers we have used here, it is an logistic regression, KNN, and decision tree, and support vector emission, and MLP. So there are 5 classifiers we have used in the layer 1, level 0, or layer 1 or level 0, whatever it is. So the next level, so we collected the probabilities of these 5 classifiers on the respective data set. So such outputs of these 5 classifiers, along with the ground truth information of the original sample, is fed to the next level or level 1 classifiers called the logistic regression, bag decision tree, and the KNN classifier. So again, the outputs of these 3 classifiers, so are along with the ground truth information of the original sample, is fed to the support vector machine. Okay, so once we are feeding such after 2 stages, passing through 2 stages, so we are feeding to the SVM. Then to improve the performance of this SVM, further we can use the optimizer algorithm, the meta-heuristic approaches here to fine-tune the hyperparameters of the SVM called C and the gamma. So basically we are dividing the data sets, bags, and these independent bags are trained on different classifiers, and these classifiers are organized in 3 different levels: level 0, level 1, level 2. In the level 0, we have used 5 classifiers. Level 2, we have used 3 classifiers. In the final level, we have used the support vector machine. And again, the support vector machine has been fine-tuned with respect to the some meta-heuristic algorithm, namely particle sum optimization. Okay. Just as this is some of the data sets we used for the experimental analysis. So not only this, you can use any other data sets for your experimental purpose. So what we did here, we have used the stacking approach along with the fine-tuning of the parameters of the support vector machine. So for this, we have used some of the meta-heuristic algorithm called PS. Okay. This is some of the how we have used the particle sum optimization in the processing of the fine-tuning of the C and gamma values of the support vector machine. Okay, so this SVM itself is have certain parameters like the C1, C2, and inertia weight, and the size of the population. And these parameters, suppose everyone knows that this parameter has to be the properly fine-tuned to achieve better performance from this algorithm. Okay? So there are the 5 hyperparameters, namely the maximum number of iterations and C1 and C2 and there's another hyperparameter called W, it's called inertia weight, and what the population size. NP is the population size, which is of the 20. Okay, so these are the problem-specific parameters for a given algorithm. So for our problem, we have find into this value to the values to the size of the population to the 20 and the inertia weight for the 0.7 and C1 and C2 is of course 1.4 and the number of iterations we carried out our experiment is the 100. Okay, so with this setup, so we run the particle sum optimization for the fine tuning of the C and gamma of the support vector mission on the observed data which is being generated by the level 2 classifiers. That is nothing but those 3 classifiers. Okay, this is what is the definition of C1, C2, and W. The W is inertia weight, and the C1 is a cognitive constant or coefficient, and the C2 is a social coefficient and the constant. If you fine tune the C1 and T2, we can fine tune the performance and PSO towards a global and optimal the solution. So in order to, before we are considering the some of the classifiers for further performance analysis, so we have initially we carried out this our all the independent classifiers, so which we were used in the experiments like loss regression, k-nearest neighbor, and support vector mission, the decision tree, and multi-layer perceptron. Okay, so for every data set. So we have the rest different classifier depending on the characteristic of the data set. So different classifier as outperformed per specific the data. In case of PID, the DI decision tree performed well. For start log hot disease data set, the support vector mission has performed well. And kidney and kidney disease for this we have used MLP was performed very well, and the breast cancer even again the support vector mission has performed well. So if you observe, these 4 classifiers or 5 classifiers have been used in the first layer of your proposed model. So the reason why we are analyzing it to identify the best classifiers among each with respect to each band. Yes, of course, there are some of the performance metrics that we have used for the analyzing the performance of different supervised models. Like accuracy, it will talk about the overall performance of your model, both with respect to positive and negative class. And sensitivity, it talks about the about the positive class, and specificity is talk about the negative class. Okay, so most of the times we do not only use accuracy, but we will also use F1 score, which is the harmonic mean of the precision and recall or sensitivity. So the sensitivity is defined as the probability of a given sample is belongs to the what is the probability that given sample belongs to the negative sensitivity of positive plus. Okay, that's why it is always TP by TP plus false negative. Okay, so when your false negatives are less, the sensitivity will become 1, almost always 100%. So similarly, there is another performance measure called F measure, which is the harmonic mean of both the sensitivity and the precision. And similar to the F1 score, the harmonic mean, so we can find a geometric score, a geometric mean for the given set of given set of precision and sensitivity. We can find out the geometric mean for the model. So these are some of the performance evaluations with respect to the accuracy. So how area under curve, because most of the case, why you consider the area under curve is if it is a data set is imbalanced, because the majority of the data sets you have taken is almost imbalanced, so that in case imbalanced data set, so there is always a biasness of because if one class is majority, then the training will also be in the bias way. So to overcome this problem, to what we can use that the appropriate performance measure we can use that clearly says about the skewness of the data. The skewness of the data is called area under curve. So we have used AUC, area under curve, as a performance measure. So which is very appropriate for the unbalanced data sets, because all the experiments we carried out on unbalanced disease data sets. So AUC is an appropriate measure for evaluating these unbalanced data sets. So we experimented, and on the four different, I can say that four different oversampling techniques like SMOT, B-SMOT, and ADASIN and all. So from this we can observe that the ADASIN is performing better for majority of the data classes and majority of the classifier. So this is a technique we feel that it will improve the balance factor of your data set. So we went with this ADASIN approach. So after applying the ADASIN, so we have removed the problem, or we somehow minimize the problem of the imbalance factor. So then once the database is almost all in it's balanced, so then we have used we carried out the performance of each and every level with the performance model with only single level and with multi levels. So we carried out. So if you those rails are here. So if you look at here, if you are using the meta classifier and along with the layer 1 classifiers, the LR is the meta classifier and the layer with all level 1 classifiers. So we are getting around 80%. So like this, we repeated for every combination of the set of classifiers to identify the best configuration. So what we did here, at the model with SVM, and where the SVM parameters are fine-tuned as having the better performance with the two layers. So what we can infer from this, that for this kind of data sets, the two levels and the final level with the SVM and with the parameters have been have fine-tuned using PS4. So PS4 fine-tuned SVM is having the best performance among all other combinations. So from this we can infer that which is nothing but which is the one we have proposed with the 3 layers is performing better for these data sets for this analysis. Okay. So these are all the stuff related to the experiments, and yeah, if you look at here, for every data set, you have the respective values you have to fine tune for the C and gamma of the SVM. So for that, so we have used the particle sum optimization for fine tuning of the optimizing the values of C and gamma of the SVM, and in those results for respective database, every data set have been tabulated in the table level. So for every data set we have carried out this, and those such data set, such values have been tabulated here. And such a model, so we have the three levels, and in the third level, the final level, if you are fine tuning the parameters of the SVM using PS4, so such model is performing, I think they have achieved nearly 90% accuracy for the diabetes data, which is a balanced, and of course imbalanced, but is not too much, not too imbalanced. So the same it has been demonstrated by the other data sets to the. So from this we can say that the data sets which have an imbalance, if you are applying, if you are undergone this the data set which is imbalanced to the ADASIN process, which is oversampling technique, and feed it to the Ensemble framework which we designed, like 5 classifiers in the level 1, 3 classifiers in the level 2, level we have SPM, then so that model will perform the better in terms of the performance when compared to the existing. Okay. So this is here we compared our proposed model with respect to the state-of-the-art Ensemble models, and this comparison is of prove that the performance of Ensemble model is better than the individual classifiers. 430. Hmm. Hmm. Right, and of course we carried out the statistical analysis, the confidence level of the 95% confidence level, and carried out with the different combination of the classifiers with respect to a proposed model. And from the table, we observed that all the probability values which we got is below the 0.05. Means our proposed model is deviating significantly than the base models of our proposed model. So this work we published in one of the essay journals, and so we can refer the following title is a novel study to optimize the screen for effective disease diagnosis. So this we can, those who are interested, we can pursue it further for the further reading. Okay. Now let us look at the another interesting. One second. One second. Yeah, this is another uh, somewhat improved version of the proposed Ensemble framework. So by using meta-heuristic algorithms. So what we did here, we have taken the data set of training data set, and we have divided into 5 bags. Let it be data bag 1, data bag 2, data bag 3, data bag 4, data 5. But these bags and have been trained on 5 different classifiers, 5 heterogeneous classifiers. So altogether with the 5 data sets and with the 5 different classifiers. So every data set has been trained on 5 different classifiers. So it means altogether we have generated a pool of 20 classifiers. So because every classifier either changed in terms, there is a difference in terms of the data set or in terms of the classifier. Like that, we have generated 20 pool classifiers, and we want to find out the best combination of these 20 classifier, so that leads to the better result. So we are interested to generate best possible combination of these 20 classifiers. So it could be of possibility that if you look at the set space of these problem, it is 2 to the power of 20. It's a very huge set space to solve this optimized problem. So we can propose, we can use some meta-heuristic algorithm like PS, genetic algorithm and all. So here we have used a genetic algorithm for solving this particular optimization problem by encoding this as a binary string of size 20, and by performing mutational crossover and all these operations. So we are able to get the near optimal solution or the best solution of your combo. What the solution is? The solution will talks about the best combination of these 20 classifiers. Okay. So of course everybody knows about the genetic algorithm, which consists of crossover and mutations operations. So every chromosome will undergo this set of operation to generate new offspring. These new offsprings are different from the original chromosomes to use it for diversify the solutions, so that you can explore to explore the possible solutions in a set space. This is the chromosome structure we have used for the encoding of the problem. So where the first 4 bits talks about the I think it's the first 4 bits talks about the data set 1, and that next 4 bit talks about the data bag 2. Similarly, data bag 3, 4, and 5, and every data bag has been trained on the 5 different classifiers. Okay, 5 different classifiers. So altogether, a chromosome of size 20 we can generate. So this is a fitness function we have used. This is a very simple fitness function, like I use the majority voting, and during the majority voting calculation, what we did here, we have NB, where an NB talks about the number of active bags. So this number of active bags, how we are calculating to demonstrate the number of active bags. So because there are data bags D1, D2, D3, so there are five bags. So to consider the data bag for the in the denominator, so at least one classifier has to be selected in for each from each data bag. Okay, suppose in the D1, suppose in the if you are talking about the chromosome size of 20, so the number of active bags will be the bags at least one. If you can consider that bag for the as active bag, at least one classifier has been is in the one classifier has been trained on the respective bag and will be in the final will be in the what I can say solution, will be the classifier is in the solution. In that case, so you can consider the classifier on which it has been trained the bag as the active bag. So here in the best case we have 5 active bags. Okay, so but some it varies from the 1 to 5. It is varies from the 1 to 5. So this is how we can calculate the number of active bags, and the numerator is talks about the ensemble score. Okay, so means we will apply the majority voting and the ensemble score. We can determine the ensemble score, and this ensemble score divided by the number of active bags will be give the fitness function of your the chromosome, and this fitness function we want to maximize so that the maximum the fitness value we can better have the solutions of your problem. So this some of the experimental studies which we carried out on the different imbalanced data sets. Of course, every imbalanced data set has been undergone to the IAASSE approach, or maybe the appropriate approach depending on the kind of data you are using. And this experiment you can repeat for the more number of iterations, and you can average. You can talk always the performance of this kind of algorithm in terms of average performance, because it is it's a kind of randomized algorithm, because every time it will generate new solutions. So how these solutions are deviating from the actual solution. So for that we can use always the performance as an average performance. We always refer the solution as the average solution. So we repeat about 20 more number of times, and then we average the values of the performance of the your model, so that then we got the around 90% accuracy on the some diabetes data set. So if you look at the second column here, it talks about the complexity of the ensemble. Means what is the size of your the final chromosome, what is the size, the number of active classifiers. And so if you look at here, in the first iteration it has selected 5 classifiers. The second iteration it has selected 9 classifiers from 20, and the third iteration is 10. So like that, if you take average, on an average, the number of classifiers are being selected out of 20 is the 8 classifiers. From then, with this 80 classifier, we are able to achieve the around 91% of the accuracy. We are using this ensemble framework. We are using ensemble framework. Okay. So this is on the different data set. These are some of the experimental results on different data sets. Okay. Of course, this is again the comparative analysis of the same proposed approach with the traditional and like bagging, boosting, and stacking approaches. Even the random forest is a kind of bagging approach. So we exit, boost, GVM, the different variants of boosting and bagging algorithms. All are comes under the ensemble framework. So when comparing with these traditional techniques and even the state-of-the-art techniques which published in recent years, is also performing well. Especially in the PID, it is significantly deviating. So nearly 20% improvement in the compared to traditional bagging approach. Okay. This reals tabulated here talks about it, our proposed model, and with the help of this metaheuristic algorithm, where finding out the suitable combination of the classifiers out of these 20 is improving the performance a lot of the different disease diagnoses, different disease data sets. Okay. Yes, sir. This work has been published in the SERB journal. It's art computing, and those who wish to refer it. So you can, the following title, you can get it in the journal and you can read it further for deeper understanding of the technique. Yes, there is another. So if you look at here, what we are trying to do, so far we are talking about the classifier selection, but we are nowhere talking about the placement of the classifier. So the placement of the classifier matters when we are talking about the multi-level ensemble framework. Suppose if you look at here in the, you are proposing in the multi-level ensemble framework, where level 1, level 2, and level 3, we are in three levels, and to these three levels is required nearly 7 classifiers, and these 7 classifiers has to be selected from the pool of 20 classifiers or some number of classifiers. Means from the outer algorithm, from outer genetic algorithm, we are trying to select the best combination of the classifiers, and these selecting the best combination selecting, which is just now discussed. So this again, we are trying to find out the placement of this best combination of the classifier, because so not only selection, the placement of this classifier will also further improve the performance. This matter a lot when you are talking about the ensemble, multi-level ensemble framework. So in case of, so to figure it out further, what we did here, we have used the nested GA algorithm concept. So again, some metaheuristic approach. In the outer GA, we try to figure out the best combination of the classifiers, and these classifiers are fed to the inner genetic algorithm, and this inner genetic algorithm is trying to find out the best combination of the classifiers on this proposed 3-level ensemble framework. Okay, so of course everybody knows the genetic algorithm of how to perform the mutation and crossover, and we not to discuss. So basically we are using the genetic algorithm, one genetic algorithm inside the another genetic algorithm. Okay, so this is the idea for how we can use this genetic metaheuristic algorithms for the identifying the best classifiers as well as the placing them in the right position. So this is some stuff, same thing, this is chromosome structures, and this is the same fitness function we have used earlier in Ensemble 4 only. And when we are experimented on different data sets using this nested genetic algorithm, when we carried out the experiments with different data sets, okay, the results are very promising, and those results are tabulated in the table 29 here. Okay, the PIMA we got near 94, WBC in the Wisconsin breast cancer is 97, and kidney disease we got 98.70, and start log heart disease we got nearly 95.10. Okay, so there is a gradually we are improving the performance by first we using metaheuristics to identify the best combination. Then we are next level we are trying to improve the performance by placing these classifiers in a proper positions. Okay, so these are some of the challenging tasks we have addressed using metaheuristic algorithms, but still there is a lot of scope here if you are choosing the identifying the classifiers or to placing of classifiers. We address this, but still there is a lot of scope for the improvising the performance of the ensemble frameworks. Okay, so that could be in terms of the optimizing the layers, and I can say identifying the suitable classifiers from a pool of classifiers, suitable classifier for your appropriate ensemble framework, and placing them in the right positions. But we did for only for the 3 levels, but this can be extended for any number of levels. But we have restricted ourselves to the limited number of classifiers. Maybe the layer 1 is consisting of only 3 classifiers. We restricted ourselves, but we can extend for any number of the classifiers. So there are a lot of scope, and there is scope for the improvisation in this ensemble frameworks by using metaheuristic algorithm. Okay, so with I hope I explained about what we did, and I shown some light on what we can do it further in this particular research domain. So guys, if you have any doubts, please let me know. So this work we published in the Taylor and Francis. It was published in Computer Method Biomechanics and Biomedical Engineering. So it recently got accepted. So it's work. Maybe in couple of days it will come online. Those who wish, they can proceed further for deeper understanding. Okay. Guys, any doubts? The guys, the presentation is over. If you have any doubts, please let me know. And
और रामा जी चाय पीना पसंद करेंगे?
5 minutes. Guys, any doubts? So audience, any doubts, please raise your queries, and I'm here to clarify doubts.
Sir,
Yeah, Bosubabu, sir, just tell me.
sorry to interrupt you, sir. Any queries?
From the participants, can you please raise any kind of queries if you have, or else we'll wind up the session.
Sir, presentation over now?
Yes, sir.
Any queries from participations?
Any queries from the participants? Seems to be like no queries. Okay, shall we wind up, sir?
Yes, yes, sir. Please wait, sir.
Thank you, Bosubabu, for the opportunity.
Sir, thank you, sir.
Sir, just give me time. We would like to propose a formal vote of thanks. With immense gratitude and pleasure, as we conclude the enlightening session on meta-heuristics role in ensembling learning, delivered by our esteemed keynote speaker at this first international conference on computing for science, engineering, and artificial intelligence, CSEAi 2023. So our conference has been a convergence of brilliant mind, innovative ideas, and the cutting-edge research, and it is with a great enthusiasm that we express our heartfelt appreciation to our keynote speaker for his outstanding contribution. So the insights shared during this session have undoubtedly enriched our understanding of the pivotal role that meta-heuristics plays in the realm of ensembling learning. So our keynote speaker demonstrated a profound command of the subject matters, unraveling the complexities of the meta-heuristics and their application in the dynamic field of ensembling learning. So the ability to bridge theory with practical applications that provide us with a roadmap for leveraging these powerful techniques in solving the real-world challenges. So we extend our sincere thanks to our keynote speaker for dedicating his time and expertise and passion to share the valuable knowledge with all of us. Thank you, sir. Thank you once again. Thank you for participants. We'll catch you on again at 4:30 p.m. for the next session. Thank you, sir.
Any queries? Okay. Participations, I request you to all, without presentation, without paper presentation, without session like attendance, we are not give the certificate. Surely, this is the, I'm requesting you to all try to understand. Attendance is mapping. Okay, try to understand. I'm frequently requesting you to try to understand. Okay, without attendance. Your attendance always be mapping. Okay, try to understand. Nearly 198 papers are accepted, but 198 papers are accepted, paid, but nearly 52 authors are presentation are attended. So due to this is the not good for us, anyone try to understand without your presentation, without your attendance during the conference days. Okay, at any case, I am not giving the certificate with any request. Try to understand. No grievances were taken from anyone. I am not released any certificate. Only who are attending the certificate, who are attending the presentation, who are attending the sessions, that certificate will be reach you. Okay. I am requesting you too much, but no response from your end. Thank you very much. Krishna Kishore Tata, tell me, sir. Fab Radio 202, what? Thank you very much, sir.